We use Castigliano's theorem to help us sort out load and deflection. For instance, if we have this complicated hook shape and we wanted to know the deflection where we are applying the load, Castigliano's is one way we could sort it out. Of course, we could use finite element analysis to do it as well, but it's always valuable to be able to compare the FEA results to a hand calculation to give you confidence in those FEA results. Now it's time for an example. As you can tell, this is taken from the book, Shigley, example 412. And this is an example of a hook that is made from round steel wire, so it's going to have a circular cross-section. And the diameter of this hook is just 2 millimeters, so it's a pretty thin hook, and we don't expect a very large centroidal axis difference. This E is going to be a very small number. The hook dimensions are as shown. L is 40 millimeters and R is 50. A force of 1 Newton is applied at C, so P is equal to 1 Newton. These are tiny forces and tiny components, but we want to use Castigliano's theorem to find the deflection out here at D. And in order for us to do that, fictitious force out there at D and do some calculations. So right off the bat, the first thing that we want to do is we want to understand what all the contributions are to the stored elastic strain energy. And so in this particular case, this is a thin wire. It has pretty long distances relative to the height. So this 40 millimeter length in here is large compared to the diameter of the wire section. So we can ignore transverse shear in that. This is going to be bending dominated for sure. In AB, we're going to have bending dominated deflection. And it pretty much appears as though in all instances we are going to simply have a bending dominated deflection, and I'm just not going to have to worry about axial or shear loads at all because the diameter of the wire is small compared to the other dimensions. So it's a long thin wire, and everything AB, BC, CD, all of those are going to be bending dominated. Now, what we need to do is we need to find the deflection way out there at point D. So we're looking for the deflection at D. And so we have to sum up all of the energies, and we want to take the derivative of those with respect to a fictitious force out there at D. So that's the crux of the matter and the way we have to think about this particular problem. So we've already said we're going to restrict this to the bending energy, but we have something else that we need to consider, and that is this eccentricity, which is the difference between the centroidal and the neutral axis locations. If it's very small, as would be the case in this 2 millimeter diameter wire, then we don't have to worry about the stress distribution for curved beam and bending. In fact, the bending energy in this case is going to be identical. It's just m squared over 2ei. But in the curved section, we have to replace dx by rd theta. There's the only difference that we happen to have. So this is for a thin curved beam. We model it just as if it is a standard prismatic straight beam. The only difference is the moment is going to depend upon the curvature. So that's all that we have to do in this particular case. So what we have to do is take this section, and we have to take note of the fact that we have this length from A to B, we have this length from B to C, and then we go from C to D. Those are the 3 segments that we got to calculate the energies. And the energy calculation in AB is pretty straightforward. For BC, it's also fairly straightforward. And for CD, let's be honest, Q is a fictitious force. And so there's no energy stored beyond the 1 Newton load. So 0 energy in segment CD. So let's not even compute the stored energy there. We just want to get the stored energy in AB and in BC. So we need to figure out U bend in segment AB. And how are we going to do that? Well, we have this hook and we have this 1 Newton downward directed force. We know that this is of length 40 millimeters. The easiest way to solve this problem is to look at this segment AB, and we're going to integrate in this direction. Now what we're trying to do is find a moment moment expression because we know that the bending energy is the integral of m squared over 2ei dx. We also know that the deflection is the partial of that bending energy with respect to q, and that's simply going to be the integral of m partial m with respect to q integrated along dx divided by ei. The 2's cancel as we take the partial derivatives. So we're integrating from 0 to L. So what we need is an expression for the moment as a function of x. When we move the force P, which is acting vertically downward, over to this segment, I have the force P acting down, and I'm going to have a moment. The magnitude of that moment is P times R. I have the force Q, the fictitious force Q, further off to the right. And if I take that force Q and move it over here to the end of the beam, I get Q, and I also get another moment, Q times 2R. What we do is simple. We write the moments as a function of x. Well, the moment as a function of x is P times R plus P times x. Well, that's a negative moment. As I move in the positive x direction, which is from the right side to the left side, I get a moment that looks like that. Likewise, I'm going to get a moment from the Q, fictitious force Q, which is just 2RQ minus QX. So my moment as a function of x is just going to be minus P times R plus x minus Q times 2R plus x. Now, if I take the partial of that with respect to q, I get that the partial is minus 2r plus x. Now I plug this moment and this partial into the equation for the deflection up here, but before I do so, I let q go to 0. If I let q go to 0, this second term disappears. So then my delta at the end of segment AB is going to be the integral of 1 over ei times m, which is minus p times quantity r plus x, times the partial of m with respect to q. That's just going to be minus 2r plus x. Changes the sign here. I integrate that with respect to x from 0 to L. And this gives me a very simple expression where I simply have the load that I'm applying divided by E times I times the quantity 2r squared L plus 3/2 L squared R plus 1/3 LQ. So there we've got the deflection at the end of component AB brought about by the fictitious load Q way off on the right. Now the next thing that we have to do is we got to get the bending energy for the segment from B to C. Now before I do that though, so I got to figure that out because then I want to find the deflection. Before I do that, I need to realize that the bending energy stored in section CD has got to be equal to 0. There's no loads to the right of the actual load, and so there's no additional stored energy. Everything to the right of the point C is just going along for the ride. So we don't need to worry about solving that part of the problem because it's just 0. So instead, we want to get the bending moment in this semicircular part where we are applying the load P. We have a radius R, and we are trying to integrate as a function of theta from theta equals 0, which is here, to theta equal pi over 2, which is up there. And so what do we have to worry about? The bending moment at any location theta is going to be P times R sine theta. But what else do I have? I got to worry about the fictitious force Q. So I've forgotten that I got to add the fictitious force over here. That's Q. And so I have that force Q, and I'm also going to have a moment which is Q times R because this segment, this fictitious force Q is placed over here and vertically downward as shown there. I got another component contribution to the moment, but the moment brought about by Q is going to be Q times R plus Q times R sine theta. So it's just Q R 1 plus sine theta. Now the total moment then is going to be the sum of these two. It's P R sine theta plus Q R 1 plus sine theta. The partial of that moment with respect to Q is going to be R 1 plus sine theta. Now that we've done that, we realize this is a fictitious force. So I'm going to let that second term in the moment be equal to 0. So once we have this total moment and this partial, we realize, of course, that we we let the fictitious load go to 0, then the deflection brought about by those in segment BC is simply going to be this 1 over EI times the integral of m times the partial of m with respect to q integrated along the arc length RD theta from 0 to pi over 2. We're going from 0 to 90 degrees. So this simply becomes 1 over EI. We plug in the m, which is p r sine theta. We plug in the partial of m with respect to q, which is r1 plus sine theta. And we have this RD theta. We're integrating that from 0 to pi over 2. We take all the terms out that aren't going to affect the integral. We get this PR cubed over EI times the integral from 0 to pi over 2 of sine theta times the quantity 1 plus sine theta integrated with respect to d theta. And that gives me a relatively straightforward integral that can be easily solved if you're good at this sort of thing. And the integral of that ends up being 1 plus pi over 4. So the deflection of BC is going to be PR cubed over EI times 1 plus pi over 4. The total deflection is simply going to be the sum of the deflections. So this is the total deflection at D is going to be the sum of the deflection in segment AB plus the deflection in segment BC. Relatively straightforward thing. When you put it all together and plug in everything, you find that the deflection is 3.5 millimeters. So that gives us the deflection at D, 3.47 millimeters, brought about by the loads that are applied to this strange wire hook.